Hello and welcome to the very first teaching online lesson here in Math 172. This is going to be about section 5.1, the first section in the textbook that we cover in this trigonometry course. Excuse me. Very first section here, and let me get this up on the screen. Yes, there we go. Okay, so Chapter 5 is the first of 4 chapters that we're going to cover in this course. Chapter 5 on trigonometric functions. Then we're also going to do Chapter 6, 7, and 10, analytic trigonometry, additional topics in trigonometry, and finally topics in analytic geometry that are related to trigonometry. So these are our 4 chapters starting with Chapter 5, and we will cover all 7 sections in this chapter. From the very first one, 5.1, angles in their measure, that is our focus in this lesson. And we will go all the way through the next 6 sections on right triangle trigonometry, trigonometric functions of any angle, graphs of the various different trig functions, and inverse trig functions, and finally some word problems and applications making good use of trigonometric functions. So that's what this chapter is about, and let's go ahead and start into this first lesson about angles and their measure. We're going to talk about what an angle is and various different ways of measuring angles. There's degrees, for instance, that everybody's familiar with, but we're also going to talk about radians, a very, very important way of measuring angles. It's different from degrees, particularly when you're using trigonometric functions. So the very word trigonometry is from 2 Greek words, trigon meaning triangle, and meter meaning measurement. And so the word itself, of course, simply means measurement of triangles. And interestingly, this is where trigonometry originated from the Greeks, and their incredibly in-depth study and analysis of triangles and, of course, other geometric figures. Their work was so excellent that works that were written by the ancient Greeks in the BC days, literally, are still used today as textbooks in various places. They did excellent work in geometry and the foundations of trigonometry. They did not, I'll mention this, they did not look at geometric figures the same way that we do. Many of you know people in different cultures think differently. We look at a triangle or a square or a hexagon and we think, oh, that's a 3-sided figure or a 4-sided figure or a 6-sided figure respectively. No, that's not how they looked at it. They looked at it like it has 3 corners or 4 corners or 6 corners, or joints as they call them, and we call them, of course, technically vertices. Each one is a vertex. These corners or joints in the Greek word was gon, G-O-N. So if it had 3 joints, it was a trigon. If it had more than that, like 6 joints, it was a hexagon, and such as that. So that's where those words come from. Well, trigonometry is an amazing subject. You can learn a little bit about it and almost instantly put the little bit that you learn to good use, or you can go much, much more in depth into it and use it for calculus and a lot of scientific applications, astronomy, navigation, surveying, lots of different applications. In the real world, trigonometry is directly applicable to things like sound waves, light rays, planetary orbits, vibrating strings, periods of pendulums such as that. And now let's talk about angles. An angle, I believe everybody has some idea of what we think of when we say the word angle, but actually, technically, geometrically speaking, an angle is the union of 2 rays. If you recall from geometry, a ray is half of a line. It goes infinitely in one direction, perfectly straight, but it has a starting point or an end point, depending on which way you look at it. And if you have two of these rays, both with the same starting point, then those two rays together comprise an angle. So typically, sort of loosely speaking, I think most of us think of an angle as that sort of space in between the two rays, but actually, technically, geometrically speaking, the angle is the union of the two rays together. The space in between that, the two-dimensional region in between the two rays, is known as the interior of the angle, and the two-dimensional area outside the two rays is the exterior of the angle. So it would be a true statement to say that an angle plus its interior plus its exterior, the sum total of those three regions is an entire two-dimensional plane. So the angle is just the two rays, and the corner of the angle, we don't usually say corner, but that's loosely speaking, the technical term is vertex. As you see here on the screen, then the two sides are considered to have an order, so to speak. We have what's called an initial side and a terminal side. Now, what does that mean? It's the conception was by the Greeks that you would start at one of these rays and, so to speak, rotate through the plane until you come to the terminal side and stop. So the conception is that you have an initial side and then you end up with a terminal side. And yes, it is actually possible that there is no movement at all. The terminal side can just be simply the initial side. In that case, you have a degree of, you have an angle of measure of 0 degrees or 0 radians, whatever it is, it's 0 measure. But with this concept of an initial side and a terminal side, then we can develop a concept of an angle being in standard position. Standard position means that an angle is located in our classic XY coordinate plane with the initial side being the positive x-axis and the vertex of the angle being exactly at the origin, at the 0, 0 point of the XY plane. You can see that the way they've designated this angle right here that I'm motioning to. The initial side is precisely the positive x-axis, starting at 0, 0 and going to the right forever. Then the terminal side is over here in quadrant 2, going out that way forever and ever. So that angle right there, composed of that initial side and terminal side, is an angle in standard position. Now, because the conception is of having an initial side and then moving around, so to speak, to the terminal side, this allows for some interesting possibilities. For instance, we could start with the initial side of this very angle and swing around here a little bit more than 90 degrees, obviously, not 180 degrees, but more than 90, and arrive at the terminal side. But I trust you can follow with me on this. If we begin at the initial side and swing around here and continue going around all the way full circle, all the way to and past the initial side, and then stop at the terminal side, if we stop there and then draw that terminal side along with the initial side, on the paper you would have the very same angle. You could not tell any difference from it. And yet the second angle you drew, for instance, if this angle right here is halfway between 90 and 180, so perhaps it's a 135 degree angle, if we actually went full circle around and wrapped around 135 degrees again past the full circle to end up at this terminal side, then 135 plus 360, we would now have an angle which is, yes, of 495 degrees. And that's okay. You can have angles of more than 360 degrees. That's okay. What that is called then, the 495-degree angle is called a coterminal angle with the 135-degree angle. They both have exactly the same shape and position when you draw them in the coordinate plane, yet one angle is much, much larger than the other. But they're coterminal because they have the same terminal side, even though their measure is not the same. Their coterminal angles always have a difference in their measure of 360 degrees or some integral multiple of 360 degrees, some multiple of 360. You can, as we're saying here, starting with the initial side, if we swing around counterclockwise, as we're doing here to create this angle here with this terminal side, anytime you go around counterclockwise like this, starting going up through quadrant 1, then perhaps on through quadrant 2, quadrant 3, quadrant 4, in that order, then we arrive at an angle that is said to have positive measure. It is a positive angle. But if we go the other direction, if we start at the initial side on the positive x-axis and swing around clockwise, first through quadrant 4, then 3, then quadrant 2, then quadrant 1, perhaps continuing on, then we have an angle of negative measure, or what we call a negative angle. And you can have both a positive and a negative angle that are coterminal. So for instance, this 135-degree angle is coterminal with 135 plus 360, or 495, or 135 plus 360 two times if you wrap around 2 full times and then stop here. And that's going to be an 855-degree angle. So you can just keep going. There's no limit to how many times you can do that. Or you could go around the other way. You could start with a negative angle at the initial side, go through 90, 180, and another 45 degrees, end up at the same terminal side, and you would have an angle of measure negative 225 degrees. So the 135-degree angle would be coterminal with an angle of measure negative 225 degrees. Now, how are we going to name our angles? Typically, angles are named either with small Greek letters, as it says here, like alpha, beta, or theta, or uppercase English letters like capital A, capital B, capital C. And then you can do that as long as you're only having one angle and it's not confusing to the reader. But if you have, for instance, in the same figure that you have drawn, if there's more than one angle sharing the same vertex, then you need to be a little more specific. You have to, for instance, designate different points on each ray of each angle and name the angle, as you may recall, using 3 letters, with the vertex letter being the letter in the middle. So let's go on to the next page here. Call up something, well, no, they don't actually have one handy right here to describe this. But if you have, for instance, hold on, yeah. If you have, for instance, on this initial side of this angle, say there is a point A, and the vertex is labeled point B, and on the terminal side we have point C, then we could call this angle ABC or angle CBA, or we can get away with just calling it angle B in this case because it's the only angle having that vertex. But if there was another angle in this same figure having a different terminal side, then we would have to call it angle ABC or CBA. You have to use all 3 letters to be specific of which angle you're referring to. Okay. And about the measure of angles. Considering that our angles are going to be in standard position, starting off with measuring angles by degrees, I trust everybody recalls, to go full circle, that's a total of 360 degrees. Every circle has 360 degrees in it. And starting then at the initial side, that means if you're going counterclockwise for positive angles, you start with a 0-degree angle dead on the positive x-axis, and then you progress from 0 to 90 degrees as you move through the first quadrant towards the terminal side. If you go all the way through the first quadrant, then you get up here to a 90-degree angle. If you continue, it's a 180-degree angle for 2 quadrants. 3 quadrants is 270 degrees. And if you go full circle, you have a 360-degree angle, which of course is coterminal with a 0-degree angle, and all the angles in between. So going from 0 to 90, you pass some key points along the way: a 30-degree angle, 45-degree angle, and a 60-degree angle. And I've been mentioning this so far, but you'll recall the 4 different quadrants of the standard coordinate plane. Quadrant 1 in the upper right, where both x and y are positive. Quadrant 2 in the upper left, where x is negative but y is positive. Quadrant 3 in the lower left, where x is negative and y is negative. And quadrant 4, where x is positive but y is negative. And the measures of the angles that have their terminal sides in each of these quadrants then are, in quadrant 1, all angles that have not made an extra wrap around the circle, of course, the initial wrap around the circle, they're all of measure greater than 0 but less than 90. The angles whose terminal side is in quadrant 2 have measure more than 90 but less than 180. If they're strictly in quadrant 3, it's greater than 180 but less than 270. Quadrant 4 is greater than 270 but less than 360. Then if you have what is known as a quadrantal angle, the word quadrant with AL after it, a quadrantal angle is an angle that ends right on one of the axes. So for instance, if it's a 0-degree angle, the initial and terminal side is the same. If it's a 90-degree angle, then the terminal side is exactly on the positive y-axis. If it's a 180-degree angle, the terminal side is exactly the negative x-axis. If it's a 270-degree angle, the terminal side is the negative y-axis. And here's a very important point. We always speak of an angle, we say it's a second quadrant angle, we'll say it's a quadrant 2 angle or a quadrant 4 angle, purely based on where the terminal side is. Because it's understood the initial side is always on the positive x-axis. So we're only referring to that angle on the basis of where its terminal side is located. So if its terminal side is in quadrant 2, it's a quadrant 2 angle. If its terminal side is in quadrant 3, it's a quadrant 3 angle. Obviously, the entire angle is not in quadrant 3. That's impossible. But it is called a quadrant 3 angle because that's where its terminal side is. So degrees is a way of measuring angles that I know everybody's familiar with. We all learned this probably in elementary school. A circle has 360 degrees. You have a right angle with 90 degrees. You have an acute angle, as we call it. That's an angle that's more than 0 but less than 90 degrees. And then you have an obtuse angle that's more than 90 but less than 180 degrees. And there's another term I want you to know. You can have an angle greater than 180 degrees. If it's more than 180 but less than 360, that's called a reflex angle. Reflex, R-E-F-L-E-X, a reflex angle. So there's acute angles, right angles, obtuse angles, and one I didn't mention also, a straight angle is the 180-degree angle. And you say, well, that's just a straight line. Yes, it is. Geometrically, a straight line and a straight angle are absolutely the same set of points. but it's called a straight angle because it's understood to have an initial side being a ray, a terminal side 180 degrees opposite from that, and sharing the same vertex. So designating some point on the line as the vertex, then that straight line is actually a straight angle, a 180 degree angle. And again, if it's more than 180 degrees, then it's a reflex angle. I don't believe your text or your homework problems will actually get into reflex angles, but I just want you to know that. So, as we said earlier, two angles are coterminal if they have the same initial and terminal sides, like 0 and 360, or 30 and 390, or 60 and 420, or whatever. Now, that I said you can add an integral multiple of 360, so n can be any integer, positive, negative, or 0, like -3, -2, -1, 0, 1, 2, 3, whatever. Multiply that times 360 and add it to your original angle, and you will have the measure of an angle that is coterminal with a 30-degree angle. So if you want to find and create some coterminal angles, you can just start with the measure of whatever one of them is, and then add or subtract 360 degrees to that. So they give you some examples of doing that here. Or you can add 360 times 2, which would be 720, or 360 times 3, which would be 1080. Or subtract those amounts, and you'll get coterminal angles. And at this point, let me pause here. Technology tip right here. This is a good thing. There could be some homework problems where you're going to have to present answers in the form of degrees, minutes, and seconds, and not just like decimal numbers of degrees, like 60.235 degrees. You may have to say, oh, this angle is 60 degrees, 29 minutes, and 45 seconds. And they talk about this right here. I want you to know also, I have posted into Moodle, just posted in today, 2 resources for everybody. There's 2 handouts, so to speak, posted into Moodle under course resources now. The third module in Moodle, and one of them is called the unit circle handout, which is just a very nice one-page chart of a unit circle showing all the measures of all the degrees in all 4 quadrants, both in degrees and radians, which we'll be talking about here in just a few minutes. And that's the unit circle handout. Then there's a second handout showing you how to use, for instance, a TI-83 or 84 calculator and convert back and forth from decimal numbers of degrees to degrees, minutes, seconds. Going to go one from one to the other or from the other to the one. It's a very potentially useful handout for you, so please make use of those. You can go to those in Moodle under course resources, and you can print those off too. Okay. Now, another concept that's nice review from geometry, angles being complementary or supplementary to each other. This is not complicated. If 2 angles are complementary, if they are, as we say, complements of each other, then their measures add to 90 degrees. The total of their 2 measures has to be exactly 90 degrees, not just close, but exactly. And so, for instance, a 30-degree angle and a 60-degree angle are complementary angles. Each one is the complement of the other one. By the way, they do not have to be next to each other. They do not have to share a common vertex. That's not necessary. One can be somewhere and the other one can be anywhere else, but as long as their measures add to 90 degrees, they're complementary. So one could be 10 degrees and the other 80 degrees, for instance. One could be 1 degree and the other 89. Now, if an angle is more than 90 degrees, it does not have a complement. So you cannot say, well, the complement for 95 degrees would be -5 degrees. No, we don't do that. I'm going to stick with positive ones. Similarly, for supplementary angles, that means you have 2 angles whose measures add to 180 degrees. So if two angles are supplements of each other, then the measure of one added to the measure of the other is exactly 180 degrees. So for instance, a 30-degree angle would have a complement of a 60-degree angle, and a 30-degree angle would have a supplement of a 150-degree angle, because those two angles would then add to the 30 and give 90 and 180 degrees respectively. Now, on to a very important new way of measuring angles. I trust for many of you this will be new. It's called radians. The term radian is a brand new way of measuring the size of an angle, the opening of an angle. And here's how the definition of radian is arrived at. So first of all, start with a circle, and then drawing the center of the circle, and then any angle that has its vertex at the center of the circle is called a central angle of that circle. Just given that the vertex of the angle is the center of the circle, then that angle with respect to that circle is called a central angle of the circle. So here's a definition of radian. 1 radian is the measure of a central angle, call it theta, that intercepts an arc on the circle, arc S, equal in length to the radius r of that circle. Algebraically, this means that theta equals s over r, where theta is measured in radians. So it's the ratio of two distances. First of all, the arc length s, and r, the radius, the length of the radius of the circle. That's the measurement of that angle in radians. So what this means is, if the arc length wrapping around a portion of the circle, starting say here at the positive x-axis and going up to this point right here, if you were to measure the length of that, if the length of that is exactly the same as the length of the radius of the circle, then the angle right here, that angle that intercepts that arc, has a measure of exactly 1 radian. So as long as the arc length S is exactly equal to r, the radius, then the measure of that angle in between there is 1 radian. If you were to wrap around the arc length such that it would be the length of 2 radii, not just 1, then the angle measure would be 2 radians. If it only the arc length S was only half the length of a radius, the angle in between the two would be 1/2 of a radian. So that's where it comes from. And what's the relationship between radians and degrees? Well, 1 radian is much larger than a degree. It's approximate. It's actually an irrational number of degrees. It's 57 degrees and some decimal. It does not come out nice and even, unfortunately. That would be nice if it did, but it doesn't do that. It's actually like 57.2957791 degrees anyway. Roughly about 57.3 degrees, approximately, not exactly, about 57.3 degrees, a little less than 60 degrees. That's a radian. But let's consider what happens here. Since by definition, the radius of a circle is the distance from the center of a circle to any point on the circle. That is what's called as 1 radius. And I trust everybody remembers the circumference of a circle, the distance around a circle, is either 2 pi r, 2 pi, the number pi, times the length of the radius, or just pi times its diameter. The diameter being the distance across the full circle through the center. And of course the diameter is 2 radii. But if you use that first one, that the circumference is 2 pi r, 2 pi times a radius, then that means if you start wrapping around the circle a distance equal to the radius and keep doing it successively over and over, you get 1 radius, 2 radii, 3 radii, 4 radii, 5 radii, 6 radii, and a little piece of another one. And so it takes exactly 6 point something something something, but that 6 point something something something, it's about 6.28 something something, is exactly 2 times the number pi. And pi is approximately 3.14, so it's approximately 6.28, but I trust you all know that pi is an irrational number. It cannot be expressed exactly as a fraction. It's impossible. So, but it can be said, this is true, that if you wrap the radius around the circle like this on its circumference, it'll go exactly 2 pi times. Even though that's an irrational number, it's a true statement. It's 2 pi times. So this means, class, this is the point. It means that every circle having 360 degrees measure also has measure of exactly 2 pi radians. So how many radians does it take to wrap around any circle? Exactly 2 pi. And 2 pi is, again, about 6.28, 6.283185307 to 9 decimal places, but exactly 2 pi, a little bit more than 6. Now, since it's 2 pi radians for 360 degrees, those two measures are equivalent. If you cut those in half, it's quite convenient because that means just pi times the number of radians, pi radians, is exactly 180 degrees, or half a circle. So half a circle is 180 degrees. It's also, instead of 2 pi radians, it's half of 2, so it's just 1 pi radians. It's just pi radians. So this gives us this conversion fact that 180 degrees equals pi radians. Now we can divide both sides of this equation, one time by 180 and another time by pi, to get these conversion factors here. To convert back and forth between degrees and radians, here's our two ratios to multiply by. If you're starting with a number of degrees and you want to convert it to radians, you multiply the number of degrees by pi over 180. And if you want to multiply a certain number of radians, I mean, if you want to convert a certain number of radians into degrees, multiply the number of radians by 180 divided by pi. And this means, because of these conversion factors that you multiply by, the number of degrees is generally going to be much bigger than the number of radians, and vice versa. The number of radians is going to be much smaller than the number of degrees, because remember, it takes over 57 degrees just to make 1 radian. Full circle is 360 degrees, but it's only a little more than 6 radians. And you can follow through these examples in the text here of converting from degrees into radians simply by multiplying by the conversion ratio. And you come up with answers like this that sound a little odd at first, maybe a little stilted, but this is how we do state these measures. For instance, 135 degrees, when you multiply by pi over 180, turns into reducing the 135 over 180, reduces to 3 over 4, and here's how we say it. We say it's 3 pi over 4 radians. For some reason, seldom is it said that's 3/4 pi. We just don't say it that way. We say 3 pi over 4. This is what's customary and conventional. Negative 270 degrees, a negative angle, times pi over 180. The 270 and the 180 reduced to 3 over 2, and so negative 270 degrees is equal to negative 3 pi over 2 radians. Similarly, negative pi over 2 radians, multiplying by the conversion factor of 180 over pi, just the flip of the pi over 180, that the pi's cancel, 180 over 2 reduces, and it turns out to be equal to negative 90 degrees. And you can similarly find complements and supplements of angles whose measures are in radians, similarly to how you can do that if the angles have measures in degrees. And they give you some examples of this right here. That's not complicated. So, brings us to our final topic of this section, the topic of linear and angular speed. This is dealing with circular motion, motion around some circle. And of course, every circle has some specific radius, so therefore it also has some specific circumference. And so we can have two concepts of motion. A linear speed concept where moving around that circle, for instance, a race car going around a circular racetrack, how fast is it moving as it goes around that circle? Or we can speak of the concept of angular speed. In a certain measure of time, what angle around the circle has this moving object traversed? So in a certain amount of time, maybe it went around a 45-degree angle, or in a certain amount of time, it went around 270 degrees, or it went around so many radians in a certain amount of time. So it's meaningful to speak of both a linear speed, as if it was a straight line motion going around the circle, of course, but a linear speed, and it's also meaningful to speak of an angular speed. So, here's your definition now of arc length. For a circle of radius r, a central angle theta in radian measure, that's key, it's got to be in radian measure, intercepts an arc of length s, the length of that arc being given by the formula s is equal to r times theta. So S equals R theta is a very simple formula to find the length of that circular arc. So given the fact that you have an angle of some given radius R, and you have some definite central angle of measure theta in radians, then you can simply multiply that number of radians times the radius itself, and that will give you the exact length of the circular arc that contains that angle. And here's a diagram illustrating this. Here's a circle with radius of 4. We have a 240-degree angle, which is not in radians, but we're wanting to find the length of this portion of the circle, this arc length S, that exactly wraps around the circle just as far as this 240-degree angle does. Okay, so to find that arc length and use our formula, S equals R theta, first thing we have to do is convert the angle measure into radians. So, step 1, take the measure of the angle given to us of 240 degrees and convert that to radians. So we take the 240 degrees and multiply it times pi over 180. Then 240 over 180 reduces to 4 over 3. So it turns out a 240-degree angle is, in radians, is 4 pi over 3. Now, using that is our theta in the formula being S equals R theta for length of the circular arc. Now we know our theta is 4 pi over 3, so we multiply that times R, the length of the circle's radius, which is 4 inches. So 4 inches times 4 pi over 3 is 16 pi over 3. That's the exact amount. But to 2 decimal places, convert 16 pi over 3 to 2 decimal places, rounds off to 16.76 inches. Notice it is an actual length with a unit of measurement, in this case inches, because the radius is 4 inches. The arc length we're going to give in inches also as 16.76. So that's the solution to that problem. You can also perhaps imagine if you were given the arc length and the angle, you could work backwards and figure out what the radius was. Or if you were given the arc length and the radius, you could use that S equals R theta formula, so to speak, backwards, and figure the measure of the angle in radians. So now that we have the concept of arc length, we can move on to linear and angular speed. And good news, using the small letter S to stand for arc length is going to be very consistent. When we use the small letter S, it will be for arc length, and when we speak of arc length, we will use the small letter S. Just as R will be reserved for radius, S will be reserved for arc length. So let's define linear speed and angular speed in terms of our variables here. So reading in this box here, considering a particle moving at a constant speed along a circular arc of radius r. If s is the length of the arc traveled in time t, then the linear speed of the particle is simply arc length divided by time. It's just s over t, because s is the distance it travels in time t. So just as if you were in a car, and if in 2 hours you drove 100 miles, your linear speed going down the highway would be 100 miles divided by 2 hours. The 100 over 2 would reduce to 50 over 1, so that would be 50 miles per hour. Well, similarly here, if you have some arc length wrapping around a circle and you're going round and around the circle, and you traverse such a distance around the circle, and that's actually a real distance, like in inches or feet or miles or meters or whatever it might be, light years if it's the galaxy, whatever your measure is, divided by some unit of time, then that is your linear speed traversing that circular path. Okay, just s divided by t. Now, angular speed. Given that theta will be the name of the angle in radian measure, that's key, it has to be in radian measure, corresponding to this arc length s, then the definition of angular speed of this particle is the measure of the central angle divided by time. So it's theta divided by time t. So the central angle that's covered in that particular time is dividing that by the time is the angular speed. So theta over t is angular speed. So here we go. Linear speed is s over t. Angular speed is theta over t. And let me point out something to you that may not be clear from the text here. A nice relationship between these two formulas. If you tie these two formulas together using the arc length definition up here of s equals r theta, you can substitute r theta for s into the linear speed formula. Since s and r theta are the same, we can take out the s of this formula and put in r theta, and then you notice that the linear speed is just r times theta divided by t. The angular speed is just theta divided by t, which means that if you were to first figure the angular speed as theta over t, you could easily derive the linear speed by just multiplying the angular speed by the radius, r. And that works 100% of the time. If you want to first find the angular speed, the angle divided by time, and then multiply it by the radius of the circle, you will get the linear speed. So, like they say here, linear speed measures how fast the particle moves, and angular speed measures how fast the angle changes. And to wrap up this very first lesson, I want to go through a couple examples with you of word problems involving linear speed and angular speed. Now let's do this together. You do have some homework problems like these. So here's example 7 on page 404 of your text, finding linear speed. And we're going to do this with regard to the second hand of a clock. So I trust you recall good old-fashioned clocks that have the 12 different numerals around the circle of the clock have an hour hand and a minute hand and a second hand. And so our objective in this problem is to find the linear speed of the outer tip of this second hand, given that the second hand of the clock is 10.2 centimeters long, so that's the radius of our circle, and we want to find the linear speed of the tip of the second hand. Well, okay, because this is a good clock that's keeping good time, then we know it takes 1 minute for that second hand to make one full revolution, as we say, of the circle of the face of the clock. It takes exactly 1 minute for one revolution. And 1 minute, of course, is 60 seconds. So every 60 seconds, the tip of this second hand sweeps one circular motion around the clock. And we know that one circular motion is exactly 2 pi radians. So here we go. In one revolution of the second hand, the arc length traveled is, using the formula from geometry for circumference, it's 2 pi r. So the arc length S in one revolution is equal to one full circumference. You remember capital C for circumference from geometry. So S equals capital C equals 2 pi r for one full revolution. And the radius, they told us, was 10.2. That's r. So 2 pi times 10.2, the arc length traveled in one full revolution is 20.4 pi centimeters. Not yet converting pi to a decimal, it's just 20.4 times pi. And as we just determined, the time required to travel one full revolution is, of course, 1 minute or 60 seconds. So in centimeters per second, the linear speed then is the distance, the arc length traveled, divided by the time it takes to travel that. So it's 20.4 pi centimeters divided by 60 seconds. And so 20.4 pi divided by 60, and converting the pi using your calculator, don't use 3.14, please. WebAssign will mark you wrong if you round pi off to 3.14. That's a useful approximation for, shall we say, lower level math classes, but not for this course. So 20.4 pi divided by 60 rounds off to 2 decimal places as being 1.07 centimeters per second. So the linear speed of that second hand going around the clock is a little more than 1 centimeter per second. It's got a second hand a little more than 10 centimeters long, and it's moving around the face of the clock at a little more than 1 centimeter per second. So that's how that can be calculated. All right, finally, a pretty neat little problem here involving both angular speed and linear speed. And here's the situation. You've got a car that has tires with 15-inch diameters. And it's going down the road at a particular speed such that each tire makes 9.3 full revolutions every single second. So the speed that it's going down the road means that its tires are spinning 9.3 times per second. And our job is two things: find the angular speed of the tire in radians per second, and then find the linear speed of the car. And we could do it in inches per second because that's what the tire dimension excuse me, is given to us in inches. Now we could give it in inches per second, but of course that's not too useful to us in most cases. We probably want to convert that to miles per hour. That would be more interesting. But anyway, let's do it as it's given to us. So first of all, find the angular speed. Well, angular speed, if you recall from the previous page, the angular speed formula, let's look at that again, is theta over t. Angle measure in radians divided by time. So going back to our problem then, we know that each revolution, each time the tire spins, that's 2 pi radians. It's a full circle, so that's 2 pi radians. And it's doing that 9.3 times per second. So in terms of how much angle it's covering every single second, it's 9.3 times 2 pi, which is 18.6 pi radians per second. That is the angular speed. 18.6 pi radians divided by 1 second is 18.6 pi radians per second. In fact, I might tell you something right here if you haven't heard this before. The word per in math means divided by. When we say, for instance, a car is traveling 50 miles per hour, that's 50 miles divided by 1 hour. And we just say it 50 miles per hour. Here, 18.6 pi radians divided by 1 second is completely proper to be read as 18.6 pi radians per second, because per means divided by. Okay, so we have their angular speed. You could enter that, for instance, into WebAssign, and you should be marked correct. Oh, by the way, when you enter things into WebAssign, if you haven't used it before, there's sort of a learning curve, learning to find the little icons for different things like pi and fractions and all this different stuff, but I would say it's fairly user-friendly if this is your first time using it. Please remember also that everybody has 5 attempts on every single homework problem. 5 attempts. So if you're still learning WebAssign's notation or how many places you're supposed to round off to, and you're still fine-tuning your answers, you've got 5 times to try each problem. So also give yourself enough time on this. Don't wait till the due date of this homework assignment, the 5.1 homework, but go ahead and be working on it ahead of time so you can take advantage of those extra attempts if need be. And also the first homework assignment of this course, this 5.1 homework, it has more problems than most of the homework assignments are going to have. I think it has 40 problems in it. But a lot of them go very, very quickly. But it does have a high number of problems. Most of your homework assignments won't have that many problems. So again, give yourself enough time to work through all these. Okay. Part B then, find the linear speed of the car. The linear speed of the tire is actually the linear speed of the car when you think about it. How fast that tire is turning, since presumably the tire is not slipping on the road, it's maintaining good smooth contact moving down the road. So the linear speed of the outer surface of the tire is exactly the same as the forward speed of the car moving down the road. That's kind of neat. So the linear speed of the tire, using our formula again, is just S over T, and S itself by the formula for arc length is just R theta. So the linear speed, as I mentioned to you a few minutes ago, is R theta over T. So it's just the radius of the tire times the angular speed, actually. And you have to be careful here. Watch this when you're doing these word problems. Please remember, word problems typically have numerous steps. Always read the problem very carefully multiple times. Don't just read a word problem one time. For instance, you get that number stuck in your head up there, 15-inch diameter tire. So you got 15 stuck in your head perhaps, and you plug that in for radius? No, the radius is not 15 inches. It's telling us the diameter of those tires are 15 inches, so the radius, of course, is half that, just 7.5 inches, 7.5 inches. So you have to be careful about things like that. So honestly, if you just multiply the angular speed of 18.6 pi radians per second times the radius of 7.5 inches, you will get, and then convert pi, of course, to a decimal, you will get this linear speed of 438.25 inches per second rounded to 2 decimal places. Again, that's rounded because pi, decimal places go forever. So please make note of how WebAssign instructs you to round if they say round to 1 decimal place or 2 decimal places or 3 decimal places or to the nearest tenth or to the nearest hundredth or to the nearest thousandth. That's the same thing as those three respectively. Please pay very careful attention to those kinds of instructions. If it does not tell you to round at all, that's kind of interesting. Oftentimes, if it doesn't tell you to round, that's an indication that the number you're supposed to enter is not a number that needs rounding. So for instance, the angular speed that we arrived at up here in part A of this example, 18.6 pi, that's actually an exact number of radians per second. It's not rounded off, 18.6 pi. But as soon as you convert pi into its decimal equivalent, 3.14159 forever, then all of a sudden you have a decimal number that needs rounding. But if it doesn't tell you anything about rounding, that could be an indication they want you to input your answer like just with pi in it, or just as a fraction, for instance. If you get a fraction like 1/3, a simple fraction like 1/3, that has a decimal equivalent where the decimals go forever. So 1/3, the decimals go 0.333333 forever and ever. How many places do you round it off to? If it doesn't tell you, and if it tells you and input an exact answer, then the answer would be 1/3, not 0.3, not 0.33333, just 1/3. So watch for things like that. And I believe that covers our first lesson here. This is our first teaching lesson for Math 172 online. These will typically be in length roughly about an hour, sometimes a little less, occasionally maybe a little more, but usually about an hour or a little bit less. And I think we've been going now about something like around 56 minutes or so. So here's an overview for you of the concepts and some of the fine particulars of this section. I really trust this will be helpful to you in doing the homework. So I'm going to leave this with you and wish you a good rest of the day. And if anybody again has any questions, please let me know. Thank you here and goodbye.